All right, hello everyone. Welcome back. Today I'm going to be talking about vector addition and subtraction. So let's get going. So here it says there's a situation. It says a stranded boat is being towed to shore by two tugboats. What is the resulting pull? Well, let's think about that. It's basically the force exerted by tugboat 1 plus the force exerted by tugboat 2, and both of them have a magnitude and direction. And so, a question that we're going to be able to answer today is how would we be able to figure this out? How would we be able to know what's the resulting overall pull? Like, what magnitude and direction is the boat going to end up going with both of these people pulling on the boat, right? This stranded boat. Okay. Oh. So let's talk about the law for addition of vectors. So basically, this law says that when we add vector A and vector B, it's found by attaching the tail of the vector B to the tip of the vector A and then connecting the starting point to the finishing point. Okay, now A plus B, the vector, is called the resultant vector. Okay, and that's important to remember that. So I'm going to give an example of this. So let's say, for example, that I'm going to start here and then I'm going to go this way. And then from there, I'm going to go this way. And I have vector A and vector B. Well, what's the resultant vector? Where did I end up, right? Let's say this is my home. We'll put H for home. Let's say this is G, the grocery store. And let's say this is S, the school. Well, if I take a trip to the grocery store and then to the school, where did I go, right? If I went, this way for this long and then I went this way for this long, I ended up here at the school, right? So the resultant vector, A plus B vector, is this vector here, right? Because I ended up at, where did I end up? At the school. Good. All right, let's also talk about how we can use parallelograms for adding up to vectors. And we can actually incorporate the sine law or the cosine law to find our resultant vector in these situations. So, I'm without going into too much detail, I'm going to give an example here. Let's say I have a parallelogram, right? Let's say I have vector A and vector B, and then here I have vector B and vector A, and we've created a parallelogram here. Well, how could I find the resultant vector? Well, let's say I didn't have enough information to find the resultant vector. I could use the sine law or the cosine law depending in order to find it. So just to review, the sine law states that sine A over A equals sine B over B. And then the cosine law states that c squared equals a squared plus b squared minus 2ab cosine of c. Okay, and keep in mind too that cosine law is actually just a variation of Pythagoras' theorem. It's basically accounting for the fact that with Pythagoras' theorem, it only works for right angles, whereas this accounts for all of them, right? So this part here, if we do end up having a right angle, it would just disappear. It's just going to go away. Why? Because the cosine of 90 degrees is just 0. So if we plugged in 90 degrees there for here, this whole term would just be 0 and it would just go away, right? So this is basically, it's a more complex version of Pythagoras' theorem that accounts for more different things. So that's an interesting thing about cosine. I won't say much more about sine law and cosine law since we already had material earlier on talking about it. So if that is something you're interested in, you go back to earlier on material. Make sure you review that if you're unfamiliar with sine law and cosine law, as it was a prerequisite skill to have to continue with the course. Okay. So the other note here is that the overall effect of the two tugboats or the two vectors is less than the sum of the individual efforts, right? So I'm going to show you what I mean by that. Let's say that I have my tugboat, TG for tugboat, and I have one going this way and one pulling this way. And we want to know what's the resultant. Well, the resultant's going to be somewhere in the middle, but it's not going to be as strong as both of them combine as just adding up these two magnitudes, right? Magnitude of A plus magnitude of B, that's not actually going to work, right? It's going to be lesser than that. And if we think about it, it's like, well, our effort isn't just to pull it this way towards the resultant vector. Some of the energy is being used against each other, right? For example, some of B's energy is going a little bit south, and then some of A's energy is going up a bit up north, right? And so just adding the magnitudes together isn't going to get us anywhere. The only time we should add the magnitudes together is if it's the same direction. So let's say we had a tugboat and someone was pulling this way and then someone else is also pulling like the exact same direction. That's when we could add up those vectors and get the answer, right? Just like if I travel 10 meters straight this way and then I travel another 10 meters straight, I will have gone 20 meters, right? That's going to be my total distance, right? My total length of my vector, of the two vectors together. And the resultant vector as well in that too. Whereas let's say I go a bit slanted, I go a little bit left to the grocery store and then I go north to somewhere else. Well, my resultant isn't going to be quite as far away from the original destination as those two put together. It's just going to be that hypotenuse, right? It's just going to be what's left. What's left between them. So consider that as well, is that keep in mind that this vector, right, of A plus B, this is shorter, right? This is a shorter distance than if I was to just add the magnitudes of B and A together. So that is not how it works. And that's a common mistake I see students make all the time, is they'll think, oh, I can just add these things together and it'll all work out. Well, no, that's not quite right. Okay, let's move on. Let's talk about subtracting vectors. So here's where we arrange the vectors from tail to tail. So for example, let's say I have vector A, and then I have vector B like this. Then A subtract B is this one, right? So here we have them tail to tail, right? Because let's say I decided to go A, I went up here, and then we subtracted B. Well, where would we end up? Right? So it's a little bit different. Here we're going to arrange tail to tail when it comes to subtracting the vectors. Okay. So here in example 1, it says given these vectors A, B, and C, which we don't actually know, we could just make up what we want. Sketch A minus B plus C. So first I'm going to make my vectors. I'm going to say let's make A a vector like this. Let's make B a vector maybe going this way, B, and let's make C go kind of like this. Okay, so let's say we do that. Well, let's start with A, right? So A goes this way, we said. A, and then minus B. So B would normally go this way, so minus B is going to be like this. So like this, and then plus C, right? So C is like this. So where do we end up? We end up right here, right? That's where we end up there. Now you could make your vectors, there's multiple answers for this. Oh, and I should specify this is A and then minus B and then C. I should label what I'm actually doing there. And then we can show that the entire thing is the resultant vector, right? So from here, because we started here, so therefore from here to here, this was our resultant vector, right? This is our A plus B plus C, right? In this situation, where did we end up? We ended up right around there, right? So we could do this in a number of different ways. We could, there's a number of different variety of ways we could arrange those. Here's another example. It says, given the rectangular prism, determine a vector in terms of A, B, and C for each of these. So again, there are going to be multiple answers. There's not just going to be one answer for a lot of them. Okay. So let's say that this vector here going this way is vector A. Let's say that vector B, is this one. And let's say that vector C is this one. Okay, well, let's try to define these using A, B, and C. Okay, so GH. Well, it looks like GH, that's this one over here. So that's the same thing as just vector A. So I'm going to write that down, vector A. Okay, what about EG? So EG, that's going from here and it's going down. So it looks like it's negative vector C, right? Because it's same direction, or sorry, same magnitude, but the direction is the opposite direction. What about CB? Okay, so to get from here to up here, well, it looks like we need to go from C to D first, and then we need to go up, right? So we need to use vector A and then vector C. So we're going to add up vector A plus vector C, because again, remember, the position is not important. It's only the magnitude and the direction that I give, any care about. Okay, now what about D? DG. Well, here we have D, and then G is all the way over here. So if we did, let's see, if we did negative A, if we went backwards for A, and then added B, we would have it. So I'm going to write that down, negative vector A plus vector B. What about CF? Well, C is here, right? I'm just going to grab a different color. C is here, right? F is where? F is all the way over here. So we're going to have to do all the vectors in some form. We're going to have to do A to get to here, and then we're going to have to do B to get to H, and then we're going to do C. We're going to have to go up all the way to F. So this one is actually going to be A plus B plus C, like that. All right, and what about D, E? Okay, well, D is all the way over here and E is all the way over here. So we're going to have to use all of them. But this time, I think we should go backwards for A, right? So we'll do negative A vector. And then we'll use B. And then we'll go up to E and use C. So plus B plus C, right? We go here. So backwards A and then forwards B. And then also forwards C, right? So again, the position we start and end at, that's not important to know which vectors to use. It's just about what the vectors do, right? A vector, think of it like a pathway that, oh, this vector takes you, it starts at a low point, goes to this point, or this vector takes you to the left this much. This vector takes you this way this much, that kind of thing is what we want to get into the habit of, as opposed to thinking of it as, oh, this vector only works in this specific place. It's like, well, no, these vectors work regardless of where we're starting, where we're ending. So that's very important. Good, very good. Let's try example 3. Example 3 says, an airplane heads due north at 300 kilometers per hour. Okay, I'm already going to write that down. North 300. Oops. Oh, 300 kilometers per hour. Okay, and meets a wind from the west at 100 kilometers an hour. Okay, so it says from the west. So if it comes from the west, which is our left, and goes to our east, which is the right, then we're going to go like that, 100 kilometers per hour, just like so. What is the resultant speed and direction of the plane relative to the ground, right? Because the plane's up in the air and it's going 300 this way, and then the wind's kind of pushing it, so the resulting vector is going to make it go this way. Because in terms of where the heading is, it's heading straight, right? It's heading straight due north, but the wind is kind of pushing it a little to the east, so it kind of gets a little bit off track, right? Because here is north, here is our east, and then here is, we'll just say S for our starting point, right? Okay, what is the resultant speed and direction of the plane relative to the ground? So the thing is, we don't know theta, and that's our main problem, is we don't know what the heck theta is. But one thing I do know is I do know 100 and 300. And I also know, since this is due north, specifically north, and then we're going directly from the west, we also know this is a right angle, which means we can use our basic trig ratios. Now, let's say you forgot that you knew it was a right angle. We could still use our other laws like sine law and cosine law, although I don't really think we don't really have enough information to use sine law, so we'd have to use cosine law after we use Pythagoras. But anyway, if we forgot that for some reason, we could use it. We could figure it out actually with the laws. But best to know when the question does allow for us to use the basic trig ratios, just because it makes our life a little bit easier. Okay, so with that said, let's first find the theta. So we know that tan theta is equal to opposite over adjacent, which is 100 over 300, or 1/3. Therefore, theta is equal to about 18 degrees. I'm rounding there to the nearest degree. Okay? All right. Now we need to find the magnitude of the resultant vector. So the magnitude of the resultant vector is equal to 100 squared plus 300 squared, right? The two legs squared, which that's going to end up being 10,000 plus 90,000, which is 100,000. Oh, which isn't that convenient. 100,000, which means we're going to get about 316.23 kilometers per hour. Awesome. So therefore, we know that the resultant vector is equal to 316.23 kilometers per hour, and it's going to be north 18 degrees to the east, right? Because we're going north, right? And then slightly that 18 degrees to the east. So we've ended up going in this direction, even though our intention was to go straight north, right? Our intention was to go straight north. That's where we tried to go, but the wind kind of pushed us off track, and the airplane actually ended up going this way, even though it was trying to go, due north. Good. Very good. All right, let's try example 4, and this will be our last example for the day. It says if the magnitude of vector u is 15 and the magnitude of vector v is 20, and the angle between them is 75 degrees, find the magnitude of u plus v and the direction of vector u plus v. So the resultant, basically, the magnitude and direction of the resultant vector. So first, I'm going to write these vectors. So here is our u vector. And keep in mind the magnitude is 15. And then here is our v vector, where the magnitude is 20. Oh, oops. Okay. And we know that we have a 75-degree angle between them. And we're going to go, oops. Keep doing this. I keep erasing things, unfortunately. Okay. $75 degrees, there we go. And I would like to know, what is u plus v, right? What is my resultant here in this situation? Okay. Well, let's figure that out. Let's do it. So first things first, how can we figure out our direction? Well, what do we know? We know that this can be made into a parallelogram, right? We know that we could have, this is our u vector again, and then this is our v vector again. And so based on that information, we can say, well, therefore, the magnitude of u plus v squared would have to be equal to 15 squared plus 20 squared minus 2 times 15 times 20 cosine of 105 degrees, right? Why is that? Well, we have to apply cosine law in order to find this because it's not a right angle triangle, or at least we don't know that it is. In fact, well, I'm pretty sure it is not, right? But, we don't know that it is a right angled triangle, so we're going to assume it isn't. And so, in order to find the magnitude, we need to therefore use sine law or cosine law. We don't have the information at this point to use sine law, so I'm going to use cosine law. Okay, so that means that this is equal to 225 plus 400 plus 155.29. And then that means that if we square root that, we're going to get 27.93. So very close to 28. Okay? Next, I'm going to use the sine law and say, well, now that we know that number, we can use sine law in order to find the direction. So I'm going to try to find this this one here. Okay. So in this case, I'm going to say that sine theta is equal over 15 must be equal to sine 105 degrees, right? Because all these three together, these two together, 75 and 105, must be 180. So that's how I figured out that must be 105 over 27.93. And then we've got to solve. And if we solve this, we'll get that theta is equal to 31.25 degrees, or even if you just round it down to 31 degrees, that's probably fine too. Oftentimes nearest degree is okay. So then we're going to say, therefore, u plus v, our resultant vector, is equal to 29.93 units. It didn't actually tell us units, so I'm just going to write units as a word. And it's going to be 31.25. And let's see, they didn't tell us which directions to use, so I will just use north, south, east, and west. I'm going to say it's east. Oops, I should have written that first. East 27.9, no, sorry, 31.25 degrees to the north. And there we have it. There we go. Awesome. All right, well, that is it. That is it for today. I will see everybody next class. Next class, we're going to be talking about scalar multiplication of the vectors. So we'll see you for that. Bye for now.